This is Magic 063, Differentiable Manifolds. I'm Kirill Mackenzie, and this podcast is about the tangents to maps at particular points. So we start off with a smooth map, capital F from M to M prime, and fix a point in the domain, M0. And I'll write M0 prime for the value of F at M0. This is basically to keep the notation a bit simpler than otherwise. So I take a tangent vector to the domain at M0. And I define what's going to be a tangent vector x prime at the point M0 prime of capital M prime. And I define that just by pulling back functions on the target to functions on the domain by use of capital F. So in fact there should be a prime on that. Let's put that in. That should be F prime. Capital X prime applied to F prime is the composite of F prime with the smooth map capital F. And it's very straightforward to check that this X prime really does obey the differentiation, the derivation property and the linearity property, and it is a tangent vector to the target manifold at M prime 0. So I'll write for this T M0 of F applied to X. And this gives a map from the tangent space to the domain, to the tangent space, to the target at the corresponding point. And this, of course, is the tangent map of F or to F at that particular point. And it's very straightforward, again, to see that it's a linear map of vector spaces. Something about notation, quite a lot of people, not everyone, but perhaps around about half of various books and papers and seminar speakers use little d of F with a subscript on the D to indicate the point. I won't do that, and I'll talk about why not in a podcast or two or three, possibly for next week or the week after at the latest. Spivak puts a star on. This is pretty good, but the star is used for so many different things, and the tangent map is really a very fundamental thing that it's perhaps a pity to use the star for this. So as I say, we'll use capital T sub M0. Properties. Basic property, the tangent map of a composite is the composite of the tangent maps. Okay, and that's straightforward to prove. If you think about it, we're just taking the pullback over a composite, and that can be done in two stages. And another property is that if you take the identity map to a manifold, M, and take the tangent of that at a point M0, then you get, of course, the identity map of the tangent space. Okay, so these two things actually are the defining properties of a functor, and the tangent map, and later on the tangent bundle map. But the tangent map is indeed a functor from smooth manifolds and smooth maps to, in this case, vector spaces and linear maps. And it's really the simplest one, the first genuine example of an interesting functor that most people meet. I'll talk a bit more about this as we go on, but if you already know something about Lie groups and Lie algebras, you know that going from the Lie group, which is a global and generally speaking it can be quite a complicated object, to the Lie algebra, the Lie algebra is always a vector space, and of course the bracket can be complicated and interesting, but nonetheless, vector spaces are easier to deal with than global Lie groups, most of the time. The same general principles true for smooth manifolds and smooth maps and their tangent maps. And we'll see quite a few examples of this as we go along. This isn't turning into a course on category theory. All you really need to know is that these two properties here define, I seem to have squiggled out in funny directions, characterize the tangent map there as a functor on smooth maps. Here's an example that comes up over and over again, and it's best to look at it carefully once, and then we can more or less forget about it and simply use it in the future. Look at a curve in the manifold, gamma, going through a point m0 at time t equals 0. Now, we know that the tangent space to R at a particular point is a copy of R itself, and we can identify elements of R with tangent vectors to R at this particular point 0, or any chosen point, of course. So I choose 1, which, if you like, is a basis vector, a basis for this one-dimensional vector space. And that corresponds to differentiating the function f, little f, at the point 0 in the direction of 1, or along 1. In other words, it's the ordinary derivative, d dt, of f at 0 plus t times 1. And of course that is just f of t. So indeed, the differential operator to which this element 1 of the tangent space corresponds is just ordinary differentiation of this real-valued function at 0. Okay. So just for the moment, I'll denote that by 1 tilde. Spivak has a 0 downstairs. We might come back and need that later on, but not now. The point is that taking the curve gamma and applying T0 to it at the tangent vector 1 tilde 1, sends capital F, a smooth function on M, to d dt of f of gamma t. And that's precisely what we've denoted earlier by gamma dot 0 of f. So we can say, in fact, that gamma dot 0, that's a tangent vector to M at the point gamma 0, is indeed just t, the tangent map, applied to gamma at the point 0, and this unit basis tangent vector. Local coordinates, back to the general case of a smooth map capital F from M to M prime, and I'll take the dimension of M to be n and the dimension of M prime to be p, and fixing a point in the domain, little m0, take a chart phi around m0 and take a chart psi around f of m0, which is the thing that I called m0 prime a couple of minutes ago. Then f in local coordinates is a smooth map, of course, from phi of u, which is an open subset of Rn, to Rp. And I can write it like this, where f tilde is the composite of psi with f with phi inverse. And I probably ought to be a little bit careful about restricting the domains so that the compositions are strictly defined. But in fact, they can always be arranged. We can restrict phi or psi as needed to open subsets. So that's fine for now. Then these charts, phi and psi, define bases in the tangent spaces, and I see I've put a phi upstairs there to indicate that this is in the domain, and I is the index for the basis vectors, and psi there. Okay. And in terms of these bases, the tangent map becomes a matrix, of course, and the matrix which it becomes is the derivative matrix of that composite. At the point, let's say x0, where x0 is phi of m0. Okay, so that's very clear cut. I see I've rather repeated things here. This is perfectly true, but in fact it's been made clear already up here. So that's about as simple and as natural as it could be. That's how to go from a smooth map to its local representative with respect to charts on domain and target, and how to go from the tangent map between the tangent spaces to the local representation in terms of the bases defined by the charts. Okay, that's all for this podcast.